Hello, my name is Jim McKeeth, and welcome to this CodeRage 10 session on Advanced MongoDB and FireDAC. So this is the second part of our MongoDB and FireDAC coverage. This one session here I've put together based on some of the demos that Dmitry's put together, and I've also made some of my own demos, but hopefully Dmitry will be joining us for the Q&A as well. Dmitry is the brains behind, the architect behind the FireDAC implementation, as well as the Mongo implementation of FireDAC, MongoDB implementation of FireDAC. So the agenda, I'm calling this the fun stuff. The first session was really more about the basics, the fundamentals of how you interact with MongoDB. This is going to be, I think, some of the fun stuff, some of the more nitty gritty. I like getting down and getting into the details, so this is a lot more fun, I think. I'll point out that the code samples are all in Object Pascal, so if you're a C++ developer, I apologize. The reality is, in the first presentation, I showed some of the differences between the C++ code and the Object Pascal code. If you know C++, these are all just properties and events on the MongoDB objects, so you know how to interact with those. You can do this. I just didn't have time to recreate all of these in C++ as well. Maybe eventually I'll be able to do that. But you can download my slides at delphi.org/coderage, or download all my samples, the new ones I've created. Most of the samples I'm showing you, maybe about half the samples I'm showing you, ship with Seattle, but you can download the rest at delphi.org/p=2053. And actually, they'll be linked to from the CodeRage as well. So what we're going to talk about indexing, query options, geospatial queries, which I think is kind of a cool thing you can do with MongoDB, where you're able to do queries based on geometry, two-dimensional geometry. Really cool. Look at aggregation and pipelines, explain what those are, how to use them, update operations, getting some meta information from the database, and then how to take advantage of local SQL with MongoDB, which is really kind of cool as well. Just like how an RDBMS uses indexing to improve query performance, the same is true for MongoDB. Internally, MongoDB uses a B tree to build the index. It's very efficient for helping to find the records you're looking for. Since all documents by default have the _ID field, there's a default index on that field as well, which is called _ID_. You can create additional indexes on any fields that you want to search for. Because MongoDB doesn't have a consistent schema, you can actually index on a field that may or may not be present in those documents, but if you do a search for it and it doesn't have that field, you're not going to find it. So it only indexes the documents that have that field present. If you want to see if your indexes are working, check out your query performance and stuff like that, there is the option to do an explain plan as well. So let's go ahead and take a look at how to do this with FireDAC. This sample shows how to work with indexes in FireDAC and MongoDB. So what we have is a collection that contains 100 documents with integer that counts up, so this is unique, and then a random string. So probably unique, maybe not, it's hard to say. But anyway, there's two fields within here, as well as the default field of the ID. Now right now, if I do a query, and this query is going to select 5 records that are in a certain range, we can see here, this is doing an explain plan, that right here, total docs examined is 100. All right, you can also come in here and see that, so here's the filter, which is looking for a range greater than 5, less than 5, and stuff like that. But you can see a lot of details about how the query ran, the time it took, etc. Since it's a small collection, it didn't take that much time, but we can still see that it did, in fact, have to look at all 100 documents. So it's a full collection scan or a full table scan from our DBMS to find this one record. And we see right now we just have one index, and this is the index ID underscore ID underscore, and this is the default index that you get on all collections. So what we can do is we can create an index on the integer field within the document. So as we've done here, we named it by int, and the index is on int right there. So now if we run the query and do explain, we can see that the total docs examined is 4. So it only had to look at the 4 documents that match that index, because it was able to look it up in the index, which is much more efficient than doing a full collection scan. So let's go ahead and drop the indexes. So we're back down just to the default index, which we can't drop. If you try and drop it, it'll give you an error and say, hey, you can't drop that index. But let's go ahead and create an index on the other field here, the string field, and we'll do an explain again. And we see this time it did have to examine all 100 documents because that field isn't in the index. The int field wasn't in the index. Now, if we instead searched on the string field, it would have found it and used the index. So another scenario to look at is we can create a compound index. So this compound index includes both string and int fields. And we'll run the query again. And again, we see that it had to examine all 100 documents. And the reason is because the index is based on both. So that index, the compound index, only works if you are looking for doing your match on both fields. Okay, so we'll go ahead and add the index again, run the explain, and we see, again, we're able to do the docs examined in 4. So there's a lot more information in this explain plan, which you can consult the MongoDB documentation to get a better understanding of how that all works. But from the purposes here, we saw that it can show us how effective our indexes are in locating documents. So let's go and take a look at the code here. Again, this is all Object Pascal, but it's all MongoDB calls. So our FireDAC calls and MongoDB calls. So hopefully it's understandable for everybody. The populate's pretty straightforward here. All we're doing is going through, making a loop, and adding 100 documents. And that's all there is to it there. The list indexes call, there is on the collection. So we've, at the constructor create event, we actually create this f call, which is the collection. So I can find the constructor here. Oh, that's not the constructor. Here it is right here. So we go through and we connect with the connection, and then we cast that to the Mongo connection and then get the environment. And then I also just made a quick reference here. This is the collection we're going to use, which is in the test database, the advanced collection. That's just for quick references. So when you see f call, that's what we're doing there, is just referencing that one collection. So the list indexes, all we do is on the collection, we say list indexes, and that gives us back a cursor to the indexes, and each index is its own document. And so you saw the output of that. I just output the straight JSON. You could bind this to a data set, and I have an example later that shows, I believe it shows that, being bound to a data set, and you can get that information in a data set to make it easier for you to deal with possibly, or you could use the JSON iterators. To drop indexes, all we do, in this case, I'm just listing the index and going through all the indexes. So this is using the iterators to find the name. And if the name is not _ID _, then we just call on the collection drop index with the name. Okay. Now, if I tried to drop _ID _, it would give me an error because you can't do that. Actually, here, I'll run that right now. You can see the error. It says method failed. You can't drop that index. So that's why that's there. You can't drop that in specific index. You can drop all the other indexes. So to create an index, you create an index, a Mongo index, and you add keys. These are the fields that you want to index. And then options, there's a number of options you can choose from here, actually. Name being one of them. You can specify if it's a unique index, if it's a sparse index, and so on and so forth. So check out the documentation there. These object wrappers that you see here really just match the documentation really well. If you go and look at the documentation, it'll say this property does this. And you're like, oh, it's right there on that object. Boom, and you can set it and you're good to go. So consult the MongoDB documentation and you'll have an understanding of how to create indexes. And it just is straightforward in the way you'd use it here from Object Pascal or C++. Again, just translate the syntax. So then when we're done, I'm just listing the indexes out. So we've created the index. We go to the collection and say, take that index object and create the index on the collection. And it creates the index on the collection. And since we've constructed this object ourselves, we have to free the object. Again, this one here is just creating the index on string. And then this one's creating the compound index. And it's just a matter of adding more keys in here. Now, the keys actually returns keys. And so this is subkeys. So if you have keys within keys because of the nested nature of MongoDB. You can do that here. You can also go to IDX dot keys and add additional keys. So you can add top level keys or child keys if they're keys of a child document, embedded document, I guess would be the term. So that's all there is for creating indexes and dropping indexes. So let's take a look at how to do an explain plan. So little nuance here. Some of the examples we saw before, we were going to a collection doing a find, and we were taking the result and putting it as a iMongo cursor. But it also returns a, I'm trying to go on the find. So the iMongo cursor also comes back as a tmongo query. So this constructs a query, but that query implements the Mongo cursor. And so if you want to access the query object in order to specify an option like explain, then you start out with this as a Mongo query. If you want to use it as just an interface, then you use the iMongo interface, but the Mongo query can be passed as a cursor here. So this takes an iMongo cursor. So basically what I'm saying is if you want to do an options, you have to cast this or reference this as a Mongo query. And then after you've gone and built the query, there is a property here called options, right there, Mongo options, that we can then come in and set some of the options for this query. So some of the options include hints, max scan milliseconds, return key, batch size. But in this case, we're using explain. And so this gives us an opportunity to tell it we want to explain. So what it's going to do is execute that query and then return us, instead of the cursor to the query, return us a cursor to the explain plan for that query. And again, this is a JSON document or a cursor to a JSON document. In this case, I'm just outputting the JSON, but you could attach this to a tmongo dataset and display it to the user in a grid. The type of index that is not unique to MongoDB, but is a very powerful feature of MongoDB, is the ability to work with geospatial indexes and queries. This allows you to work with both 2D planar geometries and 2D spherical geometries. So like the surface of the Earth. So it's two-dimensional because it's just the surface of the sphere. It doesn't allow you to work throughout the depth of the Earth and into space and stuff like that. So it would be three-dimensional geometries there. So we're just measuring two axes, x and a y, or latitude and longitude. So you can do operations, for example, to see if a point is within bounding geometry. You can see if geometries are intersecting or if things are near a point. For more information, you can check out those two links there. Again, this works just right with the MongoDB documentation. If you can read and understand that, then you can make it work within FireDAC. So frequently, if you're going to be dealing with data that has latitudes and longitudes and you might calculate distances from them, MongoDB is a good solution for that. So I'll go ahead and show you this in action, and then we'll explain how the FireDAC calls work. So first of all, if you try and query some data that does not have a geospatial index on it, you'll get an error similar to this one. Unable to execute query, yada, yada, yada. Unable to find index for GeoNear query. So we're doing a query asking for near geography, but we don't have that index on our table or on our collection. So if we take a look at this, this is our restaurants, which we saw earlier, and we have a index on ID, which is the default. We have an index on cuisine and an index on cuisine and zip code. We don't have a geospatial index. So we can actually create a geospatial index. Right here, we've created that. Now if we do a search, we see that we have a index on the address.coord, which is the coordinates, which remember is a array of latitude and longitude. So it's an array with two values in it. And if you notice, the type of index is 2D sphere. So this is saying that we're creating an index of points on a two-dimensional sphere. This is a geospatial index. Once we've done that, we can now execute this query and see that it's telling us near the point of origin, we're going from anything that's at least 100 meters and less than 200 meters away. Actually, can make this even smaller. We'll get a few more locations. There. Let's see. Go with 100. There we go. So that's everything within 100 meters of this location. And they're sorted by distance as well. So we can actually come in here and look, and I believe this one should be exactly on the spot because I grabbed its, well, not quite. I thought I grabbed one of them and put it in here for the point of origin. But anyway, it might not show up because I have this set to 1. Let's see if I do this. 0. Aha, see, look, this one here is probably going to be exactly on the spot because it has yep, see, so because I had the minimum meter set to 1, it wouldn't show up because it was less than 1 meter from that point of origin. Anyway, this is very fast. You can do an explain plan here, and it'll show you all the information I had to go through. Let's see if we can find the doc examined 130. So it ended up examining quite a few docs. But the fact it was able to do this query is pretty cool. Actually, I tried to do long ago some queries based on distances in 3-dimensional space instead of 2-dimensional space. And it's a lot of work. You had to actually do some estimation in your query to guess if it was going to be within range, and then you had to do the guesses on each individual axis. And then, so you had basically had 3 indexes on each individual axis. And then you would then calculate the distances after the fact and have to exclude some and include some. So it was a very tedious process because, anyway. So this is really cool, the fact that it can do this, and it's just built in, and it's so easy to do right from FireDAC. So let's go ahead and take a look at the code here. So our query code, we use this. I'm using this build query call. What we do here is I have a format string on this JSON string, and the way we do it is we're doing a format. We're doing matching of, so the Q match. We're looking for address.coord, and then we're using an operator here. So instead of saying equals a value, we're saying use this operator, and we're saying near sphere. And then we specify a point in geometry. So we're saying we're going to create a geometry object, a point, and then the coordinates are the coordinates that were passed in here. So we could probably put some logic in there to make sure this is a valid point, but in this case, we're just assuming that the string being passed in is correct. And then we specify a minimum distance and a maximum distance from that point, and that's it. We pass those values into it. Put that next line. So that's the way you create the query. Here's the documentation on that. The indexing is even easier. So we want to, let's list indexes. Create the index. Again, all we do is create an index like usual. This is exactly the same way we created indexes before, except the index, instead of being a 1 here, is 2D sphere. So we're saying it's a 2-dimensional spherical index. There's 2D and 2D sphere. There's actually some other index types you can do as well, but this is just one example of the way you can deal with the different index types. This is actually the default name that it uses when it creates this. So if you were to do, if I didn't specify a name, this is the name it would use. But because I'm dropping it by name explicitly, I wanted to make sure that that name was consistent. You could, if, for example, if you're creating another index on another column, or not, I'm sorry, another field without specifying a name, it would use the same format. It would be the field name and then the value here, which is usually 1. That's it. We create the index, and we've created a 2-dimensional spherical index on that coordinates data. So the coordinates data, remember, is an array with latitude and longitude, and that's the requirement in order to do the geospatial indexing. There we go. All there is to it in order to add geospatial indexing to your application working with MongoDB and FireDAC. Aggregation pipeline. This, at least for me, took us a while to get my brain wrapped around what it is, but now that I understand it, it's a really, really cool feature, very powerful and very, very useful. Basically, it's a series of stages of operations that process data. So what this does, it allows you to take the results that are coming from the MongoDB database, those documents, and modify them into a way that makes them easier to work with. The documents enter this pipeline, which goes through a series of stages, and each stage modifies those documents or works with those documents. So this is a less complex alternative to MapReduce, which MongoDB also supports MapReduce, but we're going to talk about the aggregate pipeline and some of the methods. You can take a look at the documentation there. Again, this maps directly to the way FireDAC works. So here's an example of what aggregation is, and to help you wrap your brain around it so that you understand what the purpose is. So we see here this example where it's hitting the collection of orders. And the first stage we do is a match. Okay. And so the match says looking for orders with the status of A. And then we take those and we perform a group operation on them. So there. And the group produces, groups them by customer ID and gives us a total. So if we look at the boxes here, each box represents a document. The first column there is all the orders within that collection. So we have one order right at the bottom there that's got a status of D, which we don't get because it doesn't match our match criteria. Second column there, those are the orders that match our match criteria. And then we take and group those by the customer ID, which you see there. We have A, 1, 2, 3. We have 2 of those. And then the last column there is the results. And so it's combined the sum of those first 2. So we have the customer ID and the total value. So we've added together 255 and 500 to produce that result there. And since there's only one B212, we just bring that one over. Okay, so we've done similar stuff to this in SQL. It's just a little bit different way of looking at it and has some additional functionality because of the way MongoDB works. So it's similar to some of the stuff we've done, like I said, in SQL with an RDBMS, but again, this is specific to the way MongoDB works. So let's take a look at using this in action with FireDAC. This is the MongoDB basic sample that we ship. It's called basic, but I would say probably better description would be low level because it shows some of the low level behavior, some of the low level functionality you can do with MongoDB. So let's run this real quick here. And I'm going to show these 2 operations here. The first one is going to do an aggregate with a projection. And so what we've done here, and I'll expand this out so you can see this. And then I've slightly modified this so that it shows the original data and the translated data here. But the code, as far as doing the aggregation, is going to be the same. So this is the original document that we have here. And we notice the ISBN is all together. And anyway, see how it's formatted here. So down here, we see what we've done is taken the ISBN and broken it apart. And so the ISBN contains a prefix. So ISBN has a prefix, a group, a publisher. So this is all segments of that ISBN has been broken out. So see, we have ID, title, and then ISBN becomes an embedded object here. So you could actually do the reverse of this, where you take a embedded object. So in this case here, we have author last name, and we break that out to be a top level field here. So we just took the author's last name and put that here as last name, removing the author embedded object altogether. And then we renamed copies to copies sold. So this is an example of changing the projection, changing the way the document is displayed to make the data easier to work with. So let's take a look at the code for that. It's creating the original data document here, inserts that in there, and then we perform a find on it to display it back to the user. Now this is where the aggregation takes place. So again, we go to the collection and we do .aggregate instead of .find, and we just specify the project here. So we're not doing a match, because actually here's the match, sorry. We're looking for match where copies sold is this. So if you notice this though, the match happens after the projection change. So originally this field's called copies, but we've changed it here from copies to copies sold. And so now we're able to do the match on copies sold instead of doing a head here. So this performs the aggregation of all of them and then only returns the one that matches that here. So what we've done is gone in, the new projection is going to have the title, and then we have the field called ISBN, which has it's an object where we've placed the substrings of the ISBN into individual fields. And then we have the last name, which is from the author.last. So this digs into the author object and pulls the last. And then copy sold is just copies. So this is an example of changing the projection with an aggregate pipeline. So here's an example of a aggregate redaction using the redact operation. So what we're doing is this will let you modify the resulting document based on the value of the document itself. So when we just changed the projection, all we did is applied the same change to all documents. This does let you look at the document itself and say, oh, if the document has this content, then we'll do this. If this part of the document has this in it, then we'll do this, so on. So how this works here is first we're doing a match. We're saying we're only going to deal with ones that say year 2014. So this is the unmodified version of the document. And then here we're building a conditional. And we're doing a set intersection here. And we're saying if we get more than 0 results back from the set intersection, then we're going to do the operation. So the set intersection is based on, we have an array here, and we're looking for values in the tag property. So the tag field. So here's the tag field. We're looking for STLW or G. So if we look here, we have SI and G, STLW, and TK. So out of these results here, we have the base one here because it has STLW, G, and STLW. The one that just has TK, we've left that section off. And so the result does not have that third section on it, section 3, because of this. So we have this if statement here based on the conditional, and if it's true, if then descend. So that means we take that and return it. If not, then prune, which means we exclude it. So there's actually 3 options you can do. You can do descend, prune, and keep. If you take a look at the MongoDB documentation, it explains what those are, how they work, and how to work with them. So this is an example of, I think, some pretty complex logic that you can embed in here that can change the way the document looks. And this is something that you can offload this into MongoDB, have MongoDB do this behavior, this aggregation, and then give you back the documents pruned and redacted in the way that you would like them to be. MongoDB provides operators to update existing documents. So just like you can insert documents, you can query the documents, and you can also update the documents. You can modify specific fields of an existing document or replace a document entirely. So that's a really important distinction, is you don't have to completely replace a document. You can just go in and modify some of those fields within there. And those modifications can be static values that you pass in, or they can be operations on the values that are there. So for example, you can say, increment that value, whatever it is. I don't care what it is, don't tell me, just increase the value. And all updates are atomic within the document. So you can perform an update within a document, and that's atomic. Someone won't get a dirty read from that. And if you're updating multiple documents, each document is updated individually. And so someone could read a second document before the first document, or someone could read the second document and the first document, and only one of them have been updated. So they could read it during the middle of an update, get those documents. Check out the documentation there, and let's show you a couple examples here. So this is doing an update on a collection. So we'll take a look at what's going on here. This is the collection before the update, and this is the collection after the update. Now, the only difference between these 2 documents here is the SKU. So we notice this one's ABC123, and this is 123 ABC. So here's our update operation. We're looking for a SKU of ABC123, so that means we're only going to modify the first document. And what we do here is we say we're going to modify this. So after we do the match, we're modifying it. We're going to do an increment. We'll increment the quantity by -2, so we're going to reduce the quantity by 2. We're going to change the orders to a 1. We're going to increase the orders by 1. Increase orders by 1. And then we're going to multiply the ratings by 1.01. All right, so if we look here at this, we see that the quantity has gone down by 2. So ABC123 has gone down by 2. The orders has gone up by 1, and the rating's been multiplied by 1.01. So this is an example of updating it through an increment operation. So here we're going to do an update push, which is where you're going to push values into an array. So this is the document before the update, and this is the document after the update. So Here you'll notice we have week 1, week 2, week 3, and week 4 with scores of 10, 8, 5, and 6. So what we've done is we've added 3 new scores in here, week 5, 6, and 7. So we match, we look for ID 5, we push into the quizzes array these 3 new values. In here we have a parameter that says each is true, which means we're going to put those in there. That's the default, is going to assume true. If you have multiple values, it pushes all of them in there. But then we're going to do what's called a slice. It should be slice. And the slice means we're only going to keep the first X number of elements of the sorted array. And so it's going to perform this sort operation, sort by score descending, and then only keep the first 3. So if we look here, we have week 1, week 2, and week 5. So 6, 7, 3, and 4 were all, if we look at the scores, 6, 7, 5, and 6 are all lower than 10, 8, 8, and 8. So it's inserted these 3 values in addition to the 4 that were there, sorted them by score descending, and then truncated it, sliced it out, and only kept the 3 highest scores. So that's a really good example of a complex kind of update. That's something you wouldn't, I mean, you could do it in a stored procedure language, for example, in a RDBMS, but this is a very cool because they're able to do this in expressive language here and perform this operation as part of your update. You can also retrieve some meta information from the table as well. So, for example, here I'll show you can list the columns, or I'm sorry, list the collections. Now, you might think, well, if I can list the collections, can I get the fields of the collections? Well, no, you can't, because there is no schema. The collection has no schema, but we do know that these are the collections we have. We have a books collection. We can go look at the documents within the books collection and see what fields those documents have, so we can get how the data sets are built. Grabs a certain number of documents and scans those and says, oh, these all have these fields. This is the total number of fields that they have, the maximum number of fields, and then it creates a data set based on that. That doesn't mean the next document will match those, but generally speaking, the way people implement MongoDB databases is the collections have some similarities. That's just the way it makes sense. So anyway, here you can get a list of collections. And I'll go show you the code here on this. Is right here we can say, just go to the database, F connection to the database, .list collections, and this gives you back a cursor that has all those collections in there, so that you can then take that cursor, attach it to the data set, bind it to a grid, output it to a memo, however you want to do with that as a document. You can also use the iterators on it. The other thing here I'll show you is this one here shows you how to get any current executing operations in the database, and this is by accessing the admin database. And so go into the admin database, and then we have some collections here that are specific collections to tell you information about the database. And we're executing a command on there. So we haven't even looked at this one yet, but you can do commands. You can get more information about that if you go to the Mongo database reference right here. So I wanted to create an example that showed some of the advantages of using MongoDB through a high-level abstraction like FireDAC provides. So what we have here is this has a FD Mongo query, which is defined here at the top, where we specify a database, collection, match, sort, and projection. And then we also have a local SQL on here. So what we can do is we can open MongoDB based on the MongoDB query, and then use SQL against that MongoDB result set. So let's go ahead and run this here, and then we'll talk a little bit more what's going on. So we open the MongoDB query, and here's our result set, which we can see there. And then we can say, on here, we can say where name equals subway. And now we've restricted that down. So all of this is still in effect, so we can still do our matches and our queries via the MongoDB query, or we can do it via SQL query. So some advantages to this could be where you have a situation that you can do something in SQL, but maybe you're not quite familiar with how to do it in MongoDB, or maybe you want to do a join between a MongoDB dataset and dataset obtained through a different database. So then you could do that, put those both into the local SQL and do your join across there writing SQL. So really cool that you have this functionality. Honestly, I think you can do pretty much everything through the MongoDB query format, but maybe for convenience sake, or like I said, or if you want to do like a join or give your users the ability to further refine a data set down via SQL or some sort of query formatter, you can do that here with this. So we'll look at the code really quick here. A lot of this is going to be similar to what we've seen in other demos. In the Open Mongo here, what we're doing is we have to close our local SQL connection and our Mongo query, wire everything up here, and then open it. But then one thing we do here is we go through and we look to see if any of our fields are ADTs or data sets, because these would be nested objects or arrays. And SQLite, which is the engine that runs in local SQL, doesn't support those. So it gives an error message here. I actually tried to manually remove those, and it may have been something I just couldn't figure out how to do. But so it gives an error message here and says you can't do that and aborts. Otherwise, it goes ahead and connects to the local SQL engine up, and then here's the local SQL here. So if it's not already active, then it actually fires the Open Mongo. So when you click Open SQL, and then we just execute the SQL query here. One thing I do change is I change the data source to point to either the MongoDB query or the local SQL query, depending on which one you just ran. That way you always see something in the grid down at the bottom. For more information, check out MongoDB's documentation at docs.mongodb.org. They have really good documentation, and because of the way the wrappers are written in FireDAC, the object wrappers, it makes it really, really easy to work with this. And most of the samples you'll see, which there's down there at the bottom, the link to where the samples are found, they're all Object Pascal, have a URL in there. It's like you click on a button and it says, hey, here's a bit of code here written in Object Pascal, and it has a link to the MongoDB documentation. If you go look at the MongoDB documentation, it has a sample. It explains how this works and has a sample of it. And if you look, usually the sample in the MongoDB documentation is exactly the same sample that's implemented in Object Pascal there with FireDAC. And so you can look at it and say, oh, I see this. This is exactly the same operator name. This is the same similar syntax. And you can see how things map up, and it makes it really easy to understand what's going on there. So MongoDB's great documentation, it combined with FireDAC's great implementation, makes it really easy to figure this out and get things done. I did a skill sprint recently on the MongoDB. You can take a look at that. It's going to be it's completely different material than I covered in either of these CodeRage sessions, but you can take a look at that. Also, you can also, if you missed CodeRage, the first part of this in CodeRage, you can catch the replay. There's some links to the doc wiki. The first one's the link to what's new that lists all the MongoDB links, and so it lists links to some of the different things in MongoDB. It's kind of a good index. But then we have the RAD Studio, the overview of connecting to MongoDB. We have the code examples for the MongoDB Explorer, and we have the libraries for the MongoDB wrapper. Those are just starting points. There's more in the doc wiki you can take a look at as well. And again, you can download the code samples you saw here, as well as my slides at the URLs you see up there in the upper right-hand corner. So now we're going to do live Q&A. Thanks for joining us. You can communicate with us, quality.embarcadero.com, the FireDAC forums, email either Dmitry or myself, and we'd be happy to help you out. And there's, again, the links for the code samples and the slides. And now we'll go to live Q&A, and hopefully Dmitry is able to join us here for this. So earlier I was asked if you did a query and it was querying on an item that was in an array, if it would match. And I actually just tested that, and it does match that. So if you had, for example, the restaurants had grades, and then they had mini grades, 0 or more grades, and each grade had a different value. So if you wanted to query on just find any restaurant that had a grade of 11, you could do that just by saying grade dot score :11, and it would match it up. So yeah, you just can reference it that way. But then there are other operators that say, I want restaurants that never got a grade of 11, or I want restaurants that had a grade of 11 and a grade of 12 or something along those lines. Those are all supported through the operators. The download link, which I'll jump back to that page here. So now we're going to do live MongoDB links and so right here, this 2053. It wasn't working, but it should be working now. So if it's still not working, let me know. Sorry about that. And the CodeRage, delphi.org/CodeRage has my slides available too to download there. So the download link 2053 includes the local SQL demo, the indexes demo, and the spatial query demo. The spatial query demo, I think they all use the restaurant data set, but I don't believe they actually load it up. So you need to make sure you run one of the other examples to load up the restaurant's data set, like the restaurant sample, and it will load it up, and then you can use those samples with that collection. So Alf asks, what happens if a selection is matching an expression which should contain a number, but in reality has a text string? So if I believe if I understand correctly, you're asking if you do a query and the collection has a value as a number and you query it as a string, what would happen? It won't match. It doesn't match. So interestingly, because of the way MongoDB works, you could have one document in a collection that has the score as a string and another document that has a field called score that's a number. And you could store the number 11 in both of those. And if you did a match and said, give me match score 11 as a number, it would give you the one that has a number. And if you give me match score number as a string, it would give you the ones that has a string. There probably is an operator that lets you do both. Actually, I'm pretty sure there would be a way to do that through the match format, but it would require some of the more advanced operator stuff. That book I recommended, the Instant MongoDB, really good. It's something you can read through pretty quick, and it covers a lot of details. The definitive guide is going to be more like a reference type book. So if you want to look things up, that's a good one to go with. Although the MongoDB documentation at docs.mongodb.org is really good as well for references. So the question was asked, what kind of grid components was I using to generate the cool row column span? That's actually new in both the VCL and FireMonkey standard grids. So both of the standard grids in VCL and FireMonkey support that now. So that's really cool that it does support that, I thought. Because I noticed that too. And actually, one of them I did, it was like, had like 3 or 4 levels of nesting, which MongoDB, you can have as much nesting as you want in there. Can DB Artisan and other DB Power Tool programs be used with MongoDB and other NoSQL databases, like for optimizations? I don't know, honestly. I wish I did. I showed the ER Studio one. I would suspect some of the other databases, some of the other DB gear tools do support MongoDB, but I don't know for sure. You could go to the website, though, and take a look and find that out. If there's any other questions about MongoDB and FireDAC, go ahead and type them here into the question panel. And we'll get you some answers. Otherwise, we have 20 minutes till our next session starts. Hopefully this was enough information that you can see possibly a use case where you might want to use MongoDB in the future, and you'll be confident enough to give it a shot. I found it was really easy to work with. There's great documentation. The components all seem to work really, really well. They're well put together and such. So anyway, hopefully you'll find an opportunity to at least experiment with MongoDB and put this great new feature to use.